exponents, order of operations, and variable expressions. Let's start by explaining exponents and exponential notation. Sometimes we use exponential notation to write products in a more compact form. Basically, if we have repeated multiplication with the same number, instead of writing that number, for instance, 5 times, we might write that number 1 time with an exponent. That represents how many times we were actually multiplying that number together. So in this exponential notation, 2 to the 5th power, 2 would be referred to as the base because it is the repeated factor. 5 is called the exponent, and it is the number of times that the base is used as a factor. Using that information, let's evaluate these 4 examples. So if we have 2 to the 6th power, that means we are repeating 2 6 times in multiplication. So I'll write my 6 2's with multiplication signs in between each. And using your head, using a calculator, one way or the other, we would find that 2 to the 6th power, or 2 multiplied by itself 6 times, is 64. Going to the next example, 5 to the 4th power. 5 is the base, so that's the number that's being repeated, and it will be repeated 4 times. That's what the exponent tells us. When we multiply 5 by itself 4 times, that will become 625. Again, you could go from left to right and just begin multiplying these 5's together, put all the 5's in the calculator, one way or the other, you will end up with 625. In part C, we have 9 to the 1st power. Again, 9 is the base that will be repeated, and the 1st power tells us we write it 1 time. Basically, anytime we have something written to the 1st power, we can hide that exponent. We can remove the exponent. 9 to the 1st power equals 9. They are the exact same thing. Here we have on part D a fraction raised to the 2nd power, or we would say 2/5 squared. So 2/5 is our base that's being repeated, and the exponent says it's being repeated twice. So remember the multiplication rules for fractions. We multiply the numerators together, and we multiply the denominators together. 2 times 2 is 4. 5 times 5 is 25. Now looking at the factors we started with on the left side, 25 and 4 have no common factors, so 4 over 25 is simplified, and the problem is finished. It's important to know how to use exponents because evaluating exponential expressions is one step in the order of operations. Order of operations means the way that we approach a problem that has different arithmetic operations: multiplication, division, addition, subtraction, exponential expressions, grouping symbols, and it's important that we all work every problem the same way. If we didn't, I would get one answer, you would get another answer, which seems okay inside of a math classroom, but when you have people building a bridge or sending spacecrafts into space, it's important that everyone is working every math problem the same way. So we have 4 different parts or 4 different operations, and here's the order. The first step, we perform all operations within grouping symbols first, starting with the innermost set. So sometimes if we have nested parentheses, if we have parentheses or grouping symbols inside of other grouping symbols, we start on the inside and we work our way out. Step 2, we evaluate any exponential expressions. Step 3, multiply or divide. Sometimes division will occur before multiplication. Multiply or divide in order from left to right. Number 4, we add or subtract. Again, subtraction may occur before addition. We add or subtract in order from left to right. So let's try to simplify this expression. We have 6 divided by 3 plus 5 squared. Going through our order of operations, which I will write as PEMDAS, PEMDAS, you may have seen that before. That is our order of operations abbreviated. Parentheses, exponents, multiplication, division, addition, subtraction. Starting with P, we have no parentheses or any other grouping symbols, so we can skip the P in this process. E represents exponential expressions. We do have an exponential expression, 5 squared. 5 squared is 5 times 5, the base repeated 2 times. 5 times 5 is 25. And that is the only operation that's taking place. Everything else stays exactly the same. 6 divided by 3 plus 25. We are finished with all exponents. Now we look for multiplication or division. And we see we have one instance of division. And that takes place with the 6 divided by 3. 6 divided by 3 is 2. And that's the only operation that has taken place. It's the only thing that changes. So we bring down everything else verbatim. So we have 2 plus 25. We're finished with multiplication and division. And now we look for addition or subtraction. Here we have one operation left. That is 2 plus 25, which equals 27. You can see why it's important to have an order of operations. If you would have started somewhere else, it's possible that you would not have the same exact answer. Let's try a bit lengthier example where we do have parentheses and multiple instances of different operations. Now in this example, we actually have parentheses, we have square brackets, and those parentheses are nested inside those square brackets. So we're going to start with the innermost grouping symbols. I'm going to underline those parentheses. And inside the parentheses, we see we have multiple operations. So we have to ask ourselves, will we work on the multiplication first or the addition first? When we look at our order of operations, multiplication comes before addition. So we start with the 2 times 3 inside the parentheses. Nothing else will change. 2 times 3 is 6. And we'll write everything else verbatim all the way around it. Okay, so we took care of one operation. We still have the innermost parentheses, so we have to work the last operation inside those parentheses before we can branch out anywhere else. So 6 plus 1 is 7. I'll go ahead and keep that number inside parentheses, although there are no other operations. So as far as the parentheses inside the brackets are concerned, we are finished dealing with those parentheses. We still have one number inside parentheses, but since we have worked all the operations, we've taken care of those, we can ignore those parentheses as far as our order of operations are concerned. So now we branch out to the next set of grouping symbols, the square brackets. And inside the square brackets, again, we have two different operations. We have the 5 right next to the 7 without a plus sign or a minus sign in between. That lets us know that this represents multiplication. 5 times 7. We also have a minus sign and a 10. When we look back at the original order of operations, multiplication always comes before subtraction. So we're going to take care of the 5 times 7 inside square brackets first. 5 times 7 is 35. Everything else stays the same. Still working inside the square brackets, we have an operation where you're subtracting 35 minus 10 is 25. We can go ahead and leave the square brackets, although we've taken care of every operation inside. Now, many of you will be tempted to add the 1 and 2 next. But let's not forget that the 2 beside the square brackets indicates we are multiplying 2 and 25. And multiplication always comes before addition. So we multiply 2 and 25. 2 times 25 is 50. We have one operation left, 1 plus 50, and that equals 51. We are now finished because we have one number with no operations. Here we have another example where we see what looks like a very complex fraction. We have 6 plus 9 divided by 3 in the numerator, and 3 squared in the denominator. Now this fraction, when dealing with order of operations, can be considered a grouping symbol. It groups all of the pieces of the numerator together and all the pieces in the denominator together. So I'm going to rewrite it as such. So we really have 6 plus 9 divided by 3 grouped together, so we put parentheses, divided by, remember, a fraction represents a quotient. It represents a division problem. So the numerator divided by the denominator. And I'm not going to put parentheses around the 3 squared because it is the only term that was in the denominator. If we had some addition and subtraction, we might put parentheses there just to clean it up some. So we start our order of operations, and I'll write our little acronym again, PEMDAS. The P stands for grouping symbols, and we have parentheses. So let's underline those parentheses. And inside parentheses, we have multiple operations. We have addition and we have division. Looking at our letters, PEMDAS, division comes before addition, so we divide first. Let's use a different color to denote that. So we start with 9 divided by 3, which is 3. Everything else stays exactly the same. Now you see that I may have made a mistake. You may have wanted to deal with the exponent first. If you didn't recognize you had parentheses around the numerator, make sure we put parentheses around the numerator when we rewrite the fraction. So we're still dealing with parentheses. We have parentheses around 6 plus 3. So we perform that operation. 6 plus 3 is 9. Now we can leave the 9 in parentheses. We can remove the parentheses. It really does not matter because there are no more operations taking place inside those parentheses. Now that we've taken care of all the parentheses, we go to the next order of operations, which is exponents, exponential expressions. We have one exponential expression, 3 squared. 3 squared represents 3 times 3, and 3 times 3 is 9. So that becomes 9. Everything else stays the same. We'll go ahead and drop the parentheses around the 9 on the left side. They were just for show at that point anyway. They were not necessary. And we have one more operation, 9 divided by 9, which equals 1. And we are finished. Let's look at how the order of operations is affected when we have fractions involved. We will see that we go through the same exact process regardless of if we have whole numbers, fractions, decimals, maybe negative numbers. It does not matter. So we look for parentheses or any other grouping symbols, we find none. We look for exponential expressions, we find none. We look for multiplication or division in whatever order, left to right. And we have one instance of multiplication. 3/7 times 1/3. So we start by multiplying those two fractions together. Remember, when we multiply fractions, we multiply the numerators and we multiply the denominators. 3 times 1 is 3. 7 times 3 is 21. Everything else stays the same. Now at this point, we could either try to simplify the fraction that we just performed the operation on, or we could get common denominators. Either way is fine. I like to simplify a fraction as soon as I perform an operation. So I'm going to circle this 3 over 21, and we're going to deal with it over to the side. 3 over 21. Remember, to simplify a fraction, we want to write the prime factorization of the numerator and the denominator and cancel common factors. The 3 is its own prime factorization, so 3 equals 3. 21 equals 3 times 7. Both of those numbers are prime numbers. We see that the numerator and denominator have a common factor of 3 that can be canceled. So in the numerator, we put a 1 as a placeholder, and in the denominator, we have a 7 that's left. Let's insert that back into the problem. So 3 over 21 simplified to 1 over 7 minus 1 over 7. Using our order of operations again, we see we only have one operation left, and that's subtraction. We already have common denominators, so we write that denominator one time, perform the operation with the numerators. 1 minus 1 is 0. And if you'll remember, this is a special case for Module 1. 0 divided by a non-zero number is just 0. So 0 here is the answer. Let's try another example where we have multiple operations that need to be performed on fractions. So starting with parentheses, we do see a set of parentheses with the 3/4, but inside those parentheses, there's not an operation that we can perform. We don't have 3/4 plus a number or minus a number. We just have 3/4 in parentheses. Those parentheses help us know what the base of this initial exponential expression is. So really, we can cross out the p. We look at the exponential expressions, which we've already underlined. 3/4 squared, which is 3 over 4 times 3 over 4. We multiply the numerators. 3 times 3 is 9. 4 times 4 is 16. Everything else stays exactly the same. So we are finished with all of the exponential expressions. We now look for multiplication or division. We don't have any division. We do have one instance of multiplication. So we multiply 1/4 and 5/2. 1 times 5 is 5. 4 times 2 is 8. And just like the last example, if it were possible, I would reduce 5 over 8. The 5 and 8 have no common factors, so that is a simplified fraction. We are finished with multiplication and division. And now we look at addition or subtraction. And in this case, it will only be addition with these three fractions. So we take care of our addition from left to right. So first we would add the first two fractions, 9 over 16 and 1 over 8. Remember that before we can multiply fractions, we have to have common denominators. To have common denominators, we find the least common multiple of 16 and 8. As you work that out, and to save time, I'm not going to do so, but as you work that out, you'll find that the LCD of those two numbers is 16. So the first fraction is okay. 9 over 16 won't change. It does not need an equivalent fraction. 1 over 8 does. So we multiply both numerator and denominator by 2. That would become 2 over 16. So I just wanted to write that step first so we would actually be able to add those first two fractions. Now that we have common denominators, we write 16 one time in the denominator. We add 9 and 2. That becomes 11. So we have 11 over 16 plus 5 over 8. Again, before we can add these two fractions, we need a common denominator. We already found that the least common denominator of 8 and 16 is 16. So 11 over 16 will stay the same. 5 over 8 will be written as an equivalent fraction with a denominator of 16. We do so by multiplying the top and bottom by 2. That becomes 10 over 16. So once again, we write 16 one time as the denominator. We add both numbers in the numerator. 11 and 10 are 21. And we would find rather quickly that 21 and 16 share no common factors. When 2 is broken down, the only prime factor in its prime factorization is 2. The prime factors in the prime factorization of 21 are 3 and 7. So there will be no common factors that can be canceled. So 21 over 16 is the final answer. The last part of this section will discuss evaluating algebraic expressions. And to evaluate algebraic expressions, let's define three more terms. First, we have variable. Now, a variable is a letter that represents all numbers that fit a pattern. Basically, you can think of it as an empty box in which numbers are plugged into. It's not a set value all of the time. An algebraic expression is a collection of numbers, variables, operation symbols, and grouping symbols. And to evaluate an expression, we replace a variable in an expression by a number, and then we find the value of the expression. Let's try that. So let's evaluate 7 plus 3z when z equals -3. So our first step is to replace the variable in the expression with its equivalent value. So let's rewrite 7 plus 3z as 7 plus 3. And every time I replace a variable with a number, I put that number in parentheses. That will save you lots of heartache later on, especially when you're dealing with negative numbers. So we look at our order of operations. Let's write that down again. Once we replace the variable with a value, we go through our order of operations. Parentheses, we have a set of parentheses, but there are no operations inside. So really, we have no grouping symbols that we need to worry about. We have no exponents. We do have multiplication. Remember, whenever we have a number right beside a set of parentheses, we are multiplying that number with the number that is inside parentheses. So we multiply 3 times -3, and that is -9. Now we have one more operation, which is addition. So we're finished with multiplication and division. We're adding the 7 and -9. And when we do so, that becomes -2. We'll explain in later sections how this actually works when we add a positive number and a negative number. For this step, I would expect you to use your calculator at this point. This is the last example we will see of evaluating expressions. Let's go on to the next problem type. And we'll see that it will deal with translating phrases. This is an abbreviated table of all the different phrases that represent the different operations that we have used so far: addition, subtraction, multiplication, division, and equality, or an equal sign. This is by no means an exhaustive list. That means there could be more words that represent addition. There can be more words that represent subtraction, and so on. But this will be very helpful later on in this module as well as in Module 3. If you will remember some of these terms, then you should be in really good shape when you try to translate different expressions and verbal statements into mathematical statements. So let's try to do that. We want to write these different statements as an algebraic expression, and anytime we have an unknown number or a number, we're going to use x to represent that quantity. So part A, we have 5 decreased by a number. So we start with 5. If I decrease, I am subtracting. You can go back to the previous slide or rewind the video and find that decreased by means subtract. 5 minus a number, and a number is represented by x. So 5 minus x. Part B, the quotient of a number and 12. Quotient means division. Now division we can write one of two ways. We can actually use the division symbol, or we can write it as a fraction. I will do both just so we can see that. So the quotient of a number, which is x, and 12. That would be x divided by 12. Or if we wanted to write this in fractional notation, we would write x over 12. Either of those answers would be correct. I will say that x over 12 will be more useful later on, but for this point in the game, x divided by 12 or x over 12 will work just fine. And the last example, and this is a little tricky, that's why we have included it in this video: 6 subtracted from a number. This phrase, subtracted from, has killed many dreams in developmental math. Anytime we see the phrase subtracted from, we will have to reverse the order. So here, let's write beneath reverse. It seems like this would be one of the easier phrases because it tells us what operation we're going to use, and that's subtraction. So I'm going to write my subtraction sign, but we have to reverse the order. We can't write the 6 to the left side and the number, which remember is represented by x, on the right side. We have to flip that. So we're going to write the number first, x, minus 6. It's very important that you remember whenever you see subtracted from, you must reverse the order of the quantities. Make sure that You take good notes over this video, work hard on your homework, and ask questions when you have them.